and our team is from both Columbia University and CertiK. So people here must have heard the multiple vulnerability exploits ranging from the Solidity compiler, which is still pretty immature compared to compilers using traditional industry. There are many bugs within it, and also not to mention the more high-profile DeFi hacks. For example, things happened. I remember last fall on Eminence, and those on D-Force, Acropolis, and Landing Protocol BZX, they all caused some, multi-million-dollar hacks. And the problem we need to ask the question we need to ask ourselves is that users has many needs, and all those past hacks, ranging from compiler bugs to DeFi protocol hacks on its financial models, are composed of vulnerabilities on different levels of the program. And it is very challenging to verify all those diverse properties without, laboriously switching between verification frameworks. So in this talk, we are going to solve this problem, and we are going to present that how we solve it using using an annotation system for lifting specifications, and how we use the formal EVM model and an higher level application to resolve this. Specifically, we will present 3 motivating examples composed of you see vulnerabilities at different levels. The first one is, of course, the staked voting contract, which has been used a lot in, for example, band protocol, which manages, I think, more than $100 million last year. And also, the second example is the Solidity compiler bug, which was revealed in its version 0.6.5. Which is really one about its low-level memory and storage. And the third one is going to be an example on the soundness of the financial model of automated market maker protocol, specifically Uniswap version 2. So yeah, and from those 3 motivating examples, we synthesized basically 6 kinds of desired properties. And these properties, as you can see, ranges from user-defined functional properties, which are what we usually talk about when we talk about deductive verification, and also access control requirements, control level invariants, security pattern-based vulnerabilities, which are, those 3 are usually checked by either fuzzing or static analysis. And then finally, virtual machine level properties and financial model properties. Those 2 are more like Oracle, for example, Oracle manipulation attack, which I think no current tool can easily check unless you do simulation. And another one is the virtual machine level properties, which is usually done by providing a formal model of the virtual machine and then reason step by step of the semantics, which is quite laborious to do in real life when we are auditing blockchain projects. So the first question, when we are trying to verify all those diverse properties, is to ask ourselves, with all those properties, how do we express them in the verification process? We're asking what kind of annotations we can use. So and in this one, I'm gonna take the staked voting contract as an example. So specifically in our design, SciviK's design, first you can express the contract level invariance using the annotation method, which basically inserts the specification as a pre-post and conditions. This is pretty standard. And then you can also express the pre-post conditions using the annotation with old. And also here you can see we're saying that if the user have indeed voted, we're going to revert the UEM state, which revert is a special opcode in the UEM. And if the user haven't voted before, then now the user's stakes have been have been updated, and it has also, the voted button have been pushed through. Then we also have the annotations for security pattern-based vulnerabilities. For example, here on line 8, you have this check reentrancy pattern, which basically is saying that this function is effectively callback free. So if you see on line 12, there is this transfer success, which calls an external contract, actually an ERC777 token, and asks it to transfer from the message sender to this contract. This seems to be fine, but the implementation of this ERC777 contract has not been checked, and it is just an arbitrary address that you provided, which definitely would be hacked if this contract is published to the mainnet. But what about more complex predicates? For example, in the stake voting contracts, the developer used two mappings, namely the stakers and the pref stakers mappings to simulate. Basically, use two mappings to simulate a sorted doubly linked list. And sorted doubly linked list is a very uncommon property that we see in the verification. We see in deductive verification, and so basically because it's very hard to express, and for us to express it in a way that it is easy to be verified, we have to express it inductively. So what we do here is that we leverage the use of an intermediate verification language to embed in our annotation that we can directly port some of our specifications to calc using the annotation calc. Specifically, this one is for expressing the predicate sorted doubly linked list. Then what about loop invariants? Here you can see a lottery reward function, which is used a lot. For example, I think in the Pancake swap, the largest swap on Binance, it has some farming lottery function, and also you can see this kind of lottery reward functions in actually you can also see this kind of arithmetic related loop invariants in the DAO token distribution mechanism in Uniswap version 2. So overall, this is pretty prevalent. And you can see here, the actual loop invariant for this lottery function would be, you can see here, very hard to synthesize even. And so what we did is that we provided a continuous loop network that basically leverages deep learning to synthesize those loop invariants for us. So how it works is that we provide the pre and post conditions on those loops, and then we have an annotation called learn to tag the variables that are actually going to be using the invariant, and then our tool would execute this lottery reward function, and specifically the loop, and then get all of the traces of x and y. Here you can see a loop of execution traces graph. You can see that, and basically after all those runs, when we collected enough data, we are able to learn such invariant. So up to now, we have answered our question of how do we express all those diverse properties in the verification process, saying that most properties could be expressed using the annotation system. But for those hard to express properties, we use calc, calling to calc for indexically defined complex predicates, and also the deep learning aided specification synthesis annotation. Yeah, so up to this point, we are able to prove the user-defined functional properties, the access control requirements from contract level invariants, and also the security pattern-based vulnerabilities, such as the ERC777 reentrancy attack previously presented. So now we are going to ask ourselves, how do we prove the virtual machine level properties, which are usually very low level and pretty different from the annotations we have seen in the past few slides. So the question we're gonna ask is that it's hard to check virtual machine level properties, especially those involve EVM details such as memory manipulation and at the same time keep our annotation system clean and our verification effortless. So the verification has to be effortless, because usually if you do an auditing of a smart contract project and you use the approach of EVM formalization and reason the semantics step by step, it is quite tedious. So, and we don't want that, because that is not scalable. People have to be experts to use those kind of tools. So, to resolve this problem, we basically will introduce the higher level verification technique, which first involves the introduce of solidity intermediate representation. So basically here is it's a snippet of the solidity, generated from the solidity compiler by Solidity, and with the IR, right? You can see that this language has many EVM opcodes embedded, and it also exposes all pointer arithmetic, so that it is low level enough, but it is not that low level. It still resembles some of the frankly, I would say the abstraction level is about the same as VMware. So this solidity exposes the VM operations, so that we can, as you can see here, we can we get a way to verify those virtual machine level formats. Then we also introduce another language, which is YML, which is what we are gonna to translate our program from YO into. So YML is basically this OCaml-ish language derived from the Y3 platform for deductive program verification, and it is integrated with some with multiple SMTs and the Cox improver. So this enables us to again use the calc annotation for us to export the formal model for export the formal model of the smart contract when we try to prove the complex predicates. Here is a snippet of the formalized EVM in YML. So basically, let's go back to the stake floating contract and see how in our framework we would prove its properties, and specifically the virtual machine related ones. So the voting function over here will be translated into YO, the Solidity IO, and the annotations of it, namely those about the functional correctness and the security pattern-based vulnerability, will be translated into YML. And as you can see here, since YO exposes a lot of low-level details, it's basically, a very terrifying piece of code that has, all those read from storage, and then indexing of storage, and basically it indexes variables using arithmetic numeric identifiers and calls EVM opcodes. So how do we simplify that? In our tool, we provided some formally proven lemmas about the EVM to reduce, for example, here the reading and the memory index can be reduced to just accessing some variable in the EVM. So, yeah, and then after the translation into YO, the function will be translated into YML and merged with the translated annotations, namely the ones that we just talked about, which is super complicated over here, and EVM formalization. So so over here, the voting function basically would take EVM state, and the EVM state would contain, as you can see here, the we synthesized a variable for the for the mapping data structure, and we use abstractly defined functions for retrieving the data from those mappings. So then what about the real world example, right? Since we want to check the virtual machine level properties, then here we come to the previously mentioned example of Solidity version 6.5 compiler bug, which is one about memory array creation overflow. So consider this very simple contract. You create a function f, and then you create an array of unsigned integers in EVM memory, which is pretty much common practice. People do it every. And then in our framework, we first translate this program into YO, the Solidity IR, and then you can see that since YO exposes our pointer arithmetic and also the low-level storage memory allocation, we can it exposes a function called create memory array, which you can see here takes a predefined length and then do some arithmetic operation, and basically expanding it into, or expanding the number of indexes in the array to the actual number of bytes required to allocate something. But in the create memory array function, it didn't check it didn't check the bound for the allocation of the size. So this could lead to a overflow bug when we call the allocation function inside the create memory array function. Yeah, and in our tool, after we translated this snippet from YO into YML, you can see that the translated YML functions plus the annotations here we inserted, which are checking the length boundaries and EVM formalization. Together, we catches that compiler vulnerability. Yeah. So up to here, we have answered the question of how to check virtual machine level properties that we use the intermediate verification language, namely YML, and we also and also before translating into YML, we translate the whole program. We compile the whole program into Solidity intermediate representation to expose the low-level details, and also we aid the verification, since the translated specifications would be overly complicated in YO. We aid it with the formalization of EVM, which provide all the lemmas about how to reason about storage memory and the opcodes. So the next thing we're gonna answer is that then how do we check about the financial model properties, right? In the motivating examples slide, there is very few Solidity compiler bugs because those are usually just caught in development. but for actual financial model properties, just last year, 2020, there has been $194 million. So it is pretty serious. And we did a study. Basically, the number of hacks from January to December increased multifold, I think 4x or 5x. So it's becoming more prevalent. And so the question we are asking ourselves when we want to prove financial model properties is that contrary to all those things we proved before, those vulnerabilities usually seen in high-profile DeFi attacks are really high-level and often involve mathematical reasoning. How do we verify that? A very simple example is about the for example, the BZX hack, which involves oracle manipulation and also some calculation of its distribution of liquidity provider tokens. Those are all involving automated market maker. And so we choose the example of Uniswap V2 and verify three very simple properties of it as an example. So the first one would be, for those of you who are not familiar with automated market maker, basically it is a contract that you want to exchange your tokens, you want to swap your tokens. And so naturally the first thing we want to verify is that it is actually making a market, is that the user can exchange token 0 to the protocol and vice versa. And then we also want to say that the reserve in the protocol, namely the funds, the capital that is used by this automated market maker always equals the actual liquidity it provides when the user wants to swap tokens. Then we also want to prove that basically constant product, this increasing product property, basically constant product market maker named because the product of the contract's reserve is always the same before and after the trade. But in our example, due to Uniswap version 2, it charges 3 out of 1,000 transaction fee. The product no longer stays constant, but increases slightly after each trade. So we want to prove this property. Then, but using all of the approaches we had before, we presented, the translated YML is not overly complicated. It is 2,000 lines of code, and when we solve it, we only prove the first property, and for others, solver timeouts. And then when we report the from a model into COC, we see it's just overly complicated too. Over 300,000 lines of code. So the complexity of DeFi has rendered reasoning about reasoning about not only low-level programs, but even the intermediate representations overly difficult. So what we did is that we retrofitted the output YML, and then here's a snippet of the retrofitted one. And then after the retrofitting, we have L1 and L2 both proven by SMT under 1.5 seconds, and also L3 was able to be proven using 150 lines of code of COC. Yeah. So we have answered the question of financial model properties to say that we use retrofitting and we use porting of the farm model into COC with the intermediate verification language's help. So up to now, we have tackled all those problems that we asked ourselves at the beginning of the talk. So, but what about the real world strengths of our method of checking those 6 types of properties? We conducted study on how many, like 15, 15 contracts with 158 security properties, and most of them can be automatically verified by SMT, and some of them are successfully resolved by using our retrofitting plus COG technique. So one of the future work as well many of you will be interested, is that this deep learning aided specification synthesis thing. We proved it's working, and we see that many of the loop invariants in very popular smart contracts use this kind of loop invariant. But one interesting direction would be to provide a quantitative study on how many contracts have those deep learning aidable loop invariants. And then another one, which is responding to reviewers, is to provide a formal soundness proof of our translation rules from the Solidity file into YO and then into YML. So basically, that's the talk.